Moody chart also we discussed in the last class. This is the Moody chart which was given to us by Moody's by conducting the lot of experiments, and this was published in 1944. Still the scientists use the Moody chart for finding out the friction factor for turbulent flow. This Moody chart we discussed in the last class. So, either with the help of Moody chart for turbulent flow region or with the help of laminar concept by using this chart or by using the 64 divided by Reynolds number, we can get the friction factor, and once we know the friction factor for a particular flow situation, we can find out the head loss by using the formula HF is equal to FLV square divided by 2GD, and once we know the head loss, we can decide the size of the pump required to maintain that flow rate. Now, this formula, which is HF is equal to FLV square divided by 2GD, this gives us the head loss, which is also known as major loss. Major loss. This loss comes in the category of major loss. Whenever there is a fluid flow through pipe, whether this fluid may be the water supplied to our houses or gas being supplied to our house, or gas is being transported from one end to another end, we can find out this major loss with the help of this formula. But we have some other type of minor loss also. Whenever we want to supply one fluid from one end to another end, we need to have different type of pipes, different type of fittings. So, wherever there is a change in the direction of the velocity or magnitude of the velocity, there will be some kind of loss. Generally, these losses termed as minor losses. Losses other than the major loss is known as minor loss. So, wherever the velocity is a vector quantity, so its direction or its magnitude, wherever velocity changes means direction or magnitude, there will be some loss. So, right now we are going to discuss losses due to geometrical changes. First one is losses due to sudden enlargement. So, we have a figure here. In this figure, we have a pipe which is connected to another pipe of larger diameter, and this change in diameter is here sudden. There is a sudden enlargement. So, whenever this fluid flows in this portion, in this particular these pockets, these eddies are formed and flow is said to be separated here. If you can recall the one lecture where we talked about the separation, then you can understand what is the meaning of separation. This separated fluid does not move in x direction, though all particles are supposed to move in x direction, but only in this pocket these fluid particles are circulating here. These are known as eddies formation, and these are getting circulated here. Because of that, they take lot of energy from the main fluid and getting separated and just circulating here. Because of that, some energy is lost, right. So, generally this type of sudden enlargement should be avoided, but if it is not possible to avoid this kind of sudden enlargement, then we can derive the relationship. With the help of that, we can find out that even if we have this kind of formulation for supplying fluid from one end to another end, then what kind of loss will take place due to only this sudden enlargement, right. So, to find out the head loss due to sudden enlargement, what we will have to do, we will have to employ some governing equations. So, either we will solve the NS equation, very famous equation, Navier-Stokes equation, and then we can find out what is the head loss, or another approach, since we have not discussed the NS equation. So, another approach is to have a control volume approach. In control volume approach, we select the control volume and apply some governing relationship. With the help of those governing relationship also, we can find out the head loss due to this phenomena, which is known as sudden enlargement, right. So, we select this control volume A, B, C, D, E, F, GH and A, this one AB, CD, E, F, G, H and A. So, this is our selected control volume. Now, in this selected control volume we will apply our governing relationship. So, first governing relationship is apply momentum equation. How do we apply momentum equation for control volume? Because momentum equation is for control mass. We know that force is equal to mass into acceleration. This is relationship valid for control mass for point, basically for point mass, where mass is supposed to be acting through a point. So, how can we apply the momentum equation for control volume?